So good morning, everyone. So today, before our fall break, so I want to take a very short and quick survey of our class. Actually, I did this every time when I teach this class, and just 3 questions. And if you can leave me some feedback, I appreciate very much, and so that we can help improve this class and address any of the concerns. If you have any questions or unclear about the setting or schedule of this class, you can write it down. And I will look into this feedback and summarize and perhaps address several of them, especially concerns in our class after the fall break. So yeah, let's just take a quick survey. Don't worry, that won't we won't agree down.
Oh,
Okay.
it's working pretty well.
Oh, by the way, I want to repeat again. So if you haven't started homework 2, please start it right now and also prepare a midterm report. I suppose this homework won't take your time during the fall break. I really don't want you to spend time working on them on the fall break. So if you other than the fall break, we have spent like more than 2 weeks for this. I think that should be sufficient. Yeah, for anyone who doesn't have pens, I have 2 pens here. Would you like the actual pen? Okay, great. Okay, we start to collect the feedback in 2 minutes. We use 15 minutes here. All right. Great. Okay, thanks for your time to leaving some feedback. I will look into that and take out the constructive feedback and try to address any of your concerns. Okay, thanks. And let us continue with the perception. So we're gonna quickly wrap up perception with the remaining two practical variants. So in the last lecture, we showed the Misbah Theorem. Okay? So we talked about how do we estimate the number of mistakes random perception will make, right? If the data is linearly separable. If this data is not linearly separable, what will happen to the perception?
Cycle indefinitely.
Yes. So if the data is not, remember perception is just to learn linear classifier. Right? So if the data is not linearly separable, it won't converge to a linear classifier unless you just force it quick. Right? So only when the data is indeed linearly separable, perception can guarantee you a linear classifier which after a finite number of updates. So remember, perception updates its weights and updates its weight vector only when it makes mistakes. So the number of mistakes is actually the number of updates. Right? So we talk about Misbah Theorem, and basically it has two preconditions. One is that the norm or the length of the input vectors is upper bounded by some radius r, meaning that all the input examples are inside a ball, right? Above radius r, or more general sphere of radius r. And secondly, the data is linearly separable, and there is a separating hyperplane whose margin for the data set is gamma. So you can derive the upper bound of number of mistakes as r squared over gamma squared, right? So we used 3 steps to show that theorem. So in the first 2 steps, we show 2 inequalities by induction. And in the third step, we connected these 2 inequalities while the so-called Cauchy-Squarles inequality, right? That's some inequality about cosine function definition. And then we create a third inequality about the number of mistakes t. By solving that inequality, we derive that bound, right? And that's all about the perception Misbah theorem. This is a very fundamental theorem. So this is the only theorem we requested everyone to understand it, right? To understand how to show that, how to slightly modify it. Right? And then we proceeded to the practical version of perception. Right? We talk about in practice, right? If you implement perception, what's the standard algorithm steps, right? We need to specify the number of epochs, because in practice you really don't know if the data is linear inseparable or not, right? So that's why you need to set up some stopping criteria in case that if the data set is not linear inseparable, you can still quit after running a while, right? So one epoch just means, okay, you're going to pass through this data set for once, right? And inside each epoch, we suggest you to first do the random shuffling of the examples, and then stream those examples to the perception algorithm. And this is why, because it is more random. It's avoid bias towards some specific example order to be more robust. That's the standard implementation of perception. And then we talk about margin perception. So what is margin perception?
What do you specify a bound size for the error instead of it just being like an incorrect or correct classification?
Yeah. So this is in other words, the first time we explain why we should prefer large margin classifiers, right? So remember this figure, right? So we use that to explain why we should prefer large margin hyperplanes, discrete boundaries of classifiers. The reason is that, okay, for these 2 boundaries, H1, H2, right, both can well classify the training examples. But H1 is more likely to perform well in generalization. The reason is that H1 has much larger margin than H2, right? So remember the definition of margin is the closest distance, right? Smallest distance between the training points and the discrete boundary. So H1 has much larger margin than H2, means that H1 is kind of farther away from the high density regions of the different type of examples, right? So it will be much less risky to make mistakes. Why? If you take a look at H2, right? H2 has much smaller margin, so it is more likely to pass through the high density regions for both negative examples and positive examples, right? As a consequence, H2 pass through this high density region for positive examples. So it is likely that, okay, you're going to meet some positive example in the future on the other side of the boundary, right? Why? Because these are high density regions. Some future positive example is likely to appear here, right? And in this case, H2 will make mistakes for sure. Where similar arguments can be applied for low density regions, negative examples, right? So this is a high density region for negative examples. So if you happen to predict the negative example in the future, the negative example has a very large chance to appear here, right? This is where H2 makes mistakes. But for H1, because it's far away from both high density regions for both negative examples and positive examples, right? So imagine when H1 will make mistake, right? If it makes mistake of positive examples, only when the positive examples appear here, right? So the chance that a new positive examples appears here is very low. Why? Because these are not high density regions. These are low density regions. So if you sample a new training point, a new test point, it is unlikely to appear here. It is more likely to appear here, those high density regions. That's intuitively why we should prefer a large margin classifiers, right? If you get a choice, right, you have a bunch of linear classifiers, each of which can perfectly separate positive and negative examples. Which one should we prefer? So that leads to the so-called margin perception. Right? So we just replace the triggering condition to update by this inequality. Right? So this inequality basically says, okay, the distance, left-hand side actually the distance. The distance between this training example and the current boundary is less than eta. I'm going to enforce perception to update the position of the hyperplane. Right? So finally, if it converges, it just means, okay, for every training example, you not only correctly predict their label, but also the distance between the example and the hyperplane is no less than eta. Right? So we got a classifier whose margin at least eta. Right? So that's why it's called margin perception. So the standard perception and margin perception all work well when your training data is really linearly separable. Right? But in practice, we should realize that many cases the data set is not linearly separable. Right? So like this data set, you won't be able to find any separating hyperplane which can perfectly separate positive and negative examples. In this case, how do we run separate? How do we find an optimal linear classifier? Intuitively, we want to find such a hyperplane that it has a minimum mistakes, right? Like here. So you only make 2 mistakes in predicting this 2 positive examples. You don't make any other mistakes. We will this hyperplane as the best one. However, if you want to explicitly find such a hyperplane, it is computational very expensive. So it's known as an NP-hard problem. So what is the practical solution? So here we introduce 2 variants of the perception. One is called voted perception. The basic idea we have actually briefly covered at the end of last lecture. Right? So now we're just looking into the details. So suppose we're given a training set, right? X1, Y1, X2, Y2, X3, Y3, and so on. Right? And the label is either -1 or 1. So again, we initialize our weight vector as 0, right? Again, I want to emphasize again, the weight vector is the augmented weight vector, which has already included the bias parameter. So don't get confused. And xi has been augmented with constant feature 1, so that your W transpose X actually has already included the bias term. Then then we introduce an actual counter. So this counter records the life cycle of each distinct weight vector that shows up during running of the perception. That's the idea. Right? So the voted perception will record the list of all distinct weight vectors during the running, and also their life cycles. And then the longer the life cycle you can imagine, the more training examples that weight vector can correctly predict, right? That means that weight vector is more important. But also there might be some weight vector which only correctly predicts several corner cases, right? Which are hard to predict, but mispredict many other examples. Right? We should account for that weight vector as well, although their life cycle is short. How can we do this? So Inside each epoch, of course, you can do some random shuffling before. Then we go through each training example xi by I. And then we use the current week vector to make prediction. Right? So if the prediction is wrong, meaning that I'm going to update week vector, we're going to get a new week vector. Right? So we get Wm plus 1 by adding Wm R y I xi, right? So this is an updating rule. So remember, Wm plus 1 is different from Wm. That means, okay, we create a new week vector, we're going to record this week vector, and also we set counter to be 1. Meaning that, okay, it was warned, right? It shows up. And we increase that, right? So, meanwhile, it means the previous week vector, Wm, is life cycle ends, right? Life cycle ends. So, this is the case when you make a wrong prediction. You end the life cycle of the current week vector, Wm, and then create a new week vector and set up a counter to be 1. And now, if you make a correct prediction, meaning that you do not need to create new week vector, you still maintain the current week vector. So I'm gonna increase the life cycle, right? So the counter for the Wm will increase by 1. And then we move to the next example. Right? In the next example, we do the prediction with the current week vector. Right? If it is correct, okay, we increase the life cycle by 1, the counter by 1, right? Otherwise, you're gonna end the life cycle of the current week vector. You get a new week vector again, and initialize its counter by 1. And do this again and again until you pass through all the training examples. You pass through, you go through all the big T epochs. And after all the epochs are done, we have collected a list of the distinct week vectors, right? And also the counter, which represents their life cycles. So you have a pairs of W1, C1, W2, C2 to WK, CK. Suppose you, during the whole big T epochs, you have saying K distinct week vectors. As we just discussed, right, the longer the life cycle, the more training examples the corresponding week vector can correctly predict, meaning that it is more important. But also we preserve all the week vectors who have small life cycles, because those week vectors might be better to cover the corner cases, the hard to classify cases. And then we're going to combine those different week vectors to make a prediction in the future. So suppose you are given a new input vector, how can I make prediction? It's very similar to A-levels. So we're going to use each week vector to make prediction, right? So this is a prediction score, and then we take the sign, we get a prediction, right? Either positive 1, minus 1, right? And then we assign the prediction, the predicted label of each week vector, a volt. The volt essentially is the corresponding life cycle. Right? And then we just convert the votes, the total votes for the positive prediction, total votes for the negative prediction, and pick up who wins the combat. That's the voltage perception. Any question?
So how many weight vectors do you end up with in the end, like in terms of your size of D and your number of epochs? Is it?
Yeah. So actually, only when you finish the big T epochs, you know how many distinct week vectors you're going to meet. Right? And of course, it is also determined by the choice of T. Right? If you just choose one epoch, you might have like 10 distinct week vectors, but if you choose 100, you might have 100. It really depends on the choice of T and also the data. Any other question?
Do we shuffle the epoch for every, if you shuffle the data to the epoch?
Yeah. I suggest you to do that. Although in this algorithm steps, you're not required to do that. But in practice, I suggest you to do that. Any difficulty in understanding this algorithm steps or idea? Okay, great. Yeah. So remember, those are why I should I keep trying to confirm with you about algorithm steps, because this is this is some algorithm you're gonna implement in your homework 3. So just want to ensure everyone is okay with this, right? And also everyone knows the idea. Right? So now I want to ask, what's the problem of this votive perception? Or what kind of what algorithm steps make you feel bad?
It takes a lot more space than regular perceptron because we have so many weight vectors.
Yes. Right. When I take a first look at this algorithm, I feel this is kind of stupid. Why should you keep a long list of this all weight vectors and the counts, right? It wastes a lot of storage. Of course, you have a lot of resources. You have a big computer memory. That's still feasible, right? But is there any more efficient way or more economic way to do this? So this is to our second variable. It's called average perception. So you see that average perception is extremely simple, but actually it reflects almost the same idea as the votive perception. But of course, there's some kind of difference we're going to highlight later. So now let us look at average perception. So compared to the standard perception, the average perception only introduces actual vector A, so we call average vector. So remember, A has the same dimension with the weight vector W. So here we're going to go through the training data set, DT epochs, right? Same framework, and inside each epoch, as someone pointed out, we should shuffle the data set, right? And then go through each training example X, Y, I, and if you make a wrong prediction, you're going to update weight vector following the rule. Right? And then, no matter you make prediction, no matter if prediction is correct or not, I'm going to add the current weight vector into A. This is just one actual line of code inserting into the standard perception framework. Then you just do it again, right? Going through every training example, going through every epoch, and finally, you return A as your learned weight vector to make prediction. So, what does this A essentially reflect? Let's do a little bit of analysis, right? So, if the current weight vector makes a correct prediction, now you're going to just add the same weight vector into A, right? So if this weight vector makes a correct continuously makes correct predictions, you just add the same weight vector multiple times, right? So this is essentially, suppose you have a correct predict examples for C times. This line of code essentially adds the same weight vector for C times. On the other hand, if you make a wrong prediction, you got a new weight vector, right? By adding the current weight vector, this term, right, is updating rule. And then immediately you add this new weight vector into A as well. from this, what we can see is that essentially A is just the weighted summation of, it's actually not weighted summation, it's a summation of all the distant V vectors multiplying with their life cycle. Right? Whenever a new V vector appears, right, A immediately added into A, right? And then, as long as that V vector correct to predict the example, it's just added into A. Right? So actually, the times of this V vector being added into A is rightly the life cycle. It's the same state I in defined in the voltage perception. So that's the smartness of this A, right? A actually has already integrated all the distant V vectors and also their life cycles. And then we just use this integrated vector, which we call average vector, to make prediction. So this is the score, right? If you explicitly write down what A includes, right, this is essentially you calculate the decision score of all the possible distant V vectors during running and multiply by the life cycle of this corresponding V vector. And finally, you take the sign outside. Any question? So now we can see this is a very smart strategy, right? Because you never explicitly store those distinct V vectors or create a counter for them. Everything has already been integrated into this average vector A, right? Compared to the standard perception, you only need to install an extra V vector. This is much more economic. So, of course, this is just the simplest version of average perception, and average perception also has other variants. So, but it's extremely popular, especially in applications like natural language processing. So, if you, in practice, if you prefer to use perception, I will suggest you to use average perception. It is robust and is efficient and economic. Memory economic.
Is there ever a danger that A will have overflow?
Over what?
Overflow?
Oh,
Overflow.
Yeah, that's a good question. Usually, if A, because you just add up a lot of vectors, right? It's very hard to overflow. If you multiply by a huge number, it might be toward overflow faster, but it just adds them up, it's fine. And even economic way will be like, okay, I'm gonna multiply some scaling factor. And remember, when we make a prediction, we actually only care about the sign, not the scalar, not the scale. Right? So you can enforce, say you can multiply this W by C0.1 and then add into it. Any other questions? Okay, great. So the remaining thing we need to be clear is the difference between these two variants. Right? They actually reflect the same idea. Right? We want to keep track all the distinct V vectors during the perception running, and also how many times they can make prediction, right? Their life cycles. And then we integrate them together to make prediction, so that's to get more accurate, more robust result. But in terms of prediction rule, these two methods are still different in some sense, right? We should be aware. So for voltage perception, because we explicitly record every distinct lead vector and their life cycle, Ci. So when we make prediction, we first use each distinct lead vector to get the label. So remember, we take the sign in front of their score, right? We get a label and then assign this label to the corresponding vote. Then we just compare the votes for total votes for the positive label and total votes for the negative label. That's for the voltage perception. But for average perception, because we have implicitly integrate the distinct bit vectors and their life cycles into one average vector, right? So when we make a prediction, we use the average bit vector to calculate the score. That basically that is equivalent to saying, okay, I'm gonna vote the score, not the label. So each distinct bit vector, we calculate distinct score, which is this inner product, right? And then we multiply this score with the corresponding life cycle of that bit vector. So this life cycle is the vote, right? So actually you vote for the score, not for the label. And then we just add up all the scores, all the voted scores together, and you determine the final sign of the result. And then the final prediction, right? The positive and negative is affected by the skew of the score, right? But for votive perception, actually, the final label is not determined by the skew of the score. It's just determined by how many votes for every particular predicted label. To be more concrete, we can take a look at this example. Right? So suppose we have 3 distinct bit vectors, right? And when we predict the label for a new input x, right? So the score for the first distinct bit vector, W1, is S1, and the score for the second, W2, is S2, right? And the score for the third is S3, right? So we assume, right, for simplicity, we assume, okay, their life cycles are all 1. So if we apply average prediction, right? So we're gonna add up all the 3 scores. S1 times C1, right? The score here. S1 times the life cycle C1 plus S2 times the life cycle C2 and S3 times the life cycle for 3, right? It's just S1 plus S2 plus S3, right? So if you get a positive label, it basically says that this weighted summation of the scores is non-negative. But it's likely that, suppose S1 and S2 are both negative, but S3 is positive, but absolute value of 3 is much larger than S1 plus S2. Then your final score is still positive. You give a positive prediction in the end. But what about votive perception? What about votive perception in this case? Remember, we just assume, okay, S1 is less than 0, S2 is less than 0, and S3 is bigger than 0, right? So what's the result for the votive perception? Any thought?
It's going to be negative.
Why?
There's more of them that are negative.
Yes, right? That's the difference, right? For votive perception, okay, according to W1, right, we know S1 is less than 0, then your prediction is negative, right? And similar for S2, right, your prediction is negative. But for S3, because S3 is positive, you'll have one positive prediction. So I have 2 negative predictions, 1 positive prediction, and their both are the same. So basically, you have more negative predictions than the positive prediction. The final prediction is negative. So this is the difference, right? So for the average perception, as we just said, right? Although S1 and S2 are both negative, right? But their skews are less than the skew of 3, you still end up with positive. But for voltage perception, we only vote for labels. So you got the first prediction negative, second prediction negative, right? They're both the same, right? And the third is positive. So we have a 2 negative prediction, 1 positive prediction. You end up with a negative prediction. Any question regarding the difference between the 2 variants of perception? Okay, great. So now we have finished the perception. So to summarize, perception is an online algorithm, very widely used, very easy to implement. It's pretty straightforward, and it has an updating rule, which essentially is the additive weights, right? Additive updates, right? You either you add the ground truth label multiplying the current weight vector, right, into the current multiply the current input vector into the current weight vector to get update. That's why it's called additive updates, right? And we have a very nice geometric interpretation about why these additive updates work. Right? And we have shown some theory about perception, especially the Misbah Theorem. And also, we have introduced several practical variants of perception, which can be more robust and more accurate. Yeah, so now you should be able to implement the perception algorithm. Okay, so next we're going to talk about another very classical, very powerful, and very popular classifiers. It's called the support machines. As maybe you have heard that before. This is the most popular machine learning model before neural networks. Before the neural networks got resurgence again. So even nowadays, like people are talking about artificial neural nets all the time, deep learning all the time, but in many applications, small back machines are the first choice. We're going to first use small back machines, and if it's working well, okay, we just use that. And you apply neural network only when, okay, you got a huge amount of data, you got enough computational resources, you have many GPUs, right? And you got enough time, and you can try deep neural nets. But if you have only have several hundreds of examples, you want to quickly try and say this can be resolved by some machine learning method, SVM will be the first choice. It's very likely that in this case SVM is better, robust, and simpler than neural networks. But before we introduce supply back machines, we need to know a little bit more theories or concepts in computational learning theory, because SVM is was born or invented based upon those results. So this is a perfect example showing how the development theory can motivate a great practical use for algorithm. Okay, so we're going to talk about the concept of agnostic learning and also DC dimension. So, what is agnostic learning? Right? So, we'll give a formal definition later, but it's different from the consistent learning we discussed before. Right? So, in the consistent learning, we assume, okay, you have a very powerful classifier, like decision tree. Every time you got 0 training error. But what if you cannot guarantee a 0 training error? This is called agnostic learning. If you don't have a 0 training error, can we still find a bound for the generalization error? Can we still claim some kind of sample complexity? Like, suppose you have enough number of training examples, right? And then with high chance you got a small generalization error. That's a problem what agnostic learning wants to address. And then we will introduce the concept of shattering and VC dimension. Because we'll say that in our sample complexity bound, we always use the size of the positive space to reflect the capacity or the complexity or the expressiveness of your learning model. Right? So at that time, I mean, even when we talk about consistent learner before, someone have already pointed out, what if your hypothesis space is infinite? If your hypothesis space is infinite, then logarithm size hypothesis space is infinite as well. Right? And the sample complexity bound is meaningless. And in that case, how do we properly measure the capacity or the expressiveness of your hypothesis space? Thus motivates the concept of VC dimension. Okay, let's just briefly review what we have discussed for the computational learning theory. Right? So we give the formal definition of the training error and generalization error. Generalization error is also called true error. Right? So the training error is just the number, the ratio of mistakenly predicted training examples between and for the true error or the generalization error is just the probability for any input sampled from the data distribution, you make a wrong prediction. And then we'll talk about the concept of pack learning and Occam's razor's principle. Right? So pack learning, the full name is probably approximate correctness learning. Right? So basically, it's a criteria tells us what kind of learning algorithms are favorable in practice. Right? So if you still, it's better that you have still have a rough impression about definition. So basically, it says that okay, the number of training examples is polynomial to a few design parameters, and then it can guarantee with high chance your learning algorithm find a hypothesis whose true error is less than some given threshold. And also we studied a very simple case, a very ideal case, which we refer to as consistent learning. Right? So here's the conclusion. Right? So let big H be any hypothesis space. Right? So we have a consistent learner, meaning that okay, whatever training data are given, it always can find a hypothesis which perfectly predict every training example. Meaning you have zero training error all the time. Then we claim that with probability, if we claim that if your training set has the size m, which is bigger than this, then with probability at least 1 minus delta, your learned hypothesis will have true error less than epsilon. Right? That's the result we have derived before. Okay? And this is called the sample complexity bound. Right? The lower bound of sample complexities, of course, this lower bound is determined by the designated the chance level and also the error level epsilon. Right? And also the size of hypothesis space. So from the sample complexity bound, we can say why the Occam's razor is good, right? We justify the Occam's razor because given the same epsilon delta, right? And the more complex the model you have, that means the larger the sample, the hypothesis space, then the more examples you need to achieve the same generalization error with the same chance. So these are about what you have discussed about computational learning theory so far. Right? Now, the underlying assumptions for those results are two aspects, right? The first, training and test examples come from the same data distribution, right? This is for sure. And although those data distributions are quite complicated, they might even don't have any analytical form, right? We don't know the form, but we usually assume okay, they are coming from the same underlying data distribution. Right? And second thing, this is about the consistent learner. So the consistent learner essentially requires that for any target function, here we use concept, right, to represent the same thing, right? there is some function in the hypothesis space which is consistent with the training set. Only if you satisfy this, you can guarantee your training error is always 0, right? Remember, this is a requirement of the consistent learner, right? So you assume that, okay, no matter what training set you have, you always find a hypothesis in a hypothesis space which can perfectly predict all the training examples. That gives 0 training error, right? How can we do that? Right? You need to ensure every target function must be inside the hypothesis space, right? If the target function is outside the hypothesis space, you'll always find a data set, a training set, where no matter what kind of hypothesis you find, you cannot give 0 training error. Right? But we can see that this assumption is kind of too ideal, right? What if my target function or the true concept is outside of this hypothesis space? Actually, it's pretty common because in many practical applications, you don't know what type of the target function is, right? For example, if you want to predict the temperature for tomorrow, right? You don't know what's the target function. Is it a polynomial function? Is it a sine function, cosine function, or their combination? We have no idea, right? And now, right now, suppose, okay, you're gonna use a linear regression model to predict that. Do you guarantee that your target function is inside your linear regressor hypothesis space? No, right? So a more practical assumption should be, okay, I allow the target function or the concept is outside your hypothesis space. So this is called agnostic learning. Why is it agnostic? Because I don't know if my hypothesis space is large enough to include the concept. Using a hypothesis space, big H, but I can be outside of big H. So any question in the understanding of the agnostic learning setting? Is everyone comfortable with that? Okay, so everyone is good with this definition, right? Okay, then the problem is, we know that this agnostic learning setting obviously is more realistic, right, than our prior consistent learning setting. But the problem we're interested in remains unchanged. So can we say something about sample complexity? Can we get some guarantee about the generalization error? There's still some critical problems we want to address. So, but before we proceed to those questions, we need to be aware in the agnostic learning setting, we no longer guarantee we can train a model with 0 training error. Why? Why we cannot guarantee we get a 0 training error?
The training set is bad.
The training set is what?
It's not good. It's so bad.
Let us assume training set is possibly good, possibly bad.
The real functions outside of our hypothesis space, so we can't actually make it match the data. the function that we're using.
Yeah, right? So remember, this is a key difference from consistent learning, right? So the real target function or real concept outside hypothesis space, right? So that means there must be some data set, right? Where every hypothesis in the hypothesis space won't get a perfect match with what the target function predicts, right? If this target function is inside the hypothesis space, well, maybe you can guarantee about zero training error. But it's outside, right? You can always find data set, right? No one in the hypothesis space can make perfect prediction, meaning that the consistent prediction made by the target function outside. So that's why, agnostic learning, usually we can now say, okay, we got zero training error all the time. But that does not mean we do not want to lower the training error. The training principle will still be, okay, I try to find a hypothesis in a hypothesis space which can be as close to the ground truth or the concept as possible. It is reflected in the fact that we're trying to minimize the training error as much as possible. Conceptually, it is to say, okay, because I'm restricted in this hypothesis space, right? So I'm trying to find a hypothesis which as close to this concept as possible. This might be here, right? And accordingly, the hypothesis here should make a low training error, right? Although not zero training error. And I also expect that, okay, even find this approximation to this target concept, our generalization errors will be good as well. Based on this, we can still expect our agnostic learning can give us a good generalization error. Any questions so far? Is that good? Okay, so here is just the definition of the training error. I just want everyone to review. So suppose you have M training examples and S is your training set, right? So the training error is actually the number of the examples in the training set which are misclassified by your learned hypothesis, right? Divided by number of training examples. This is the training error. The fraction of training examples that are misclassified. So again, the goal of the agnostic learning still is to find a classifier in the hypothesis space that has a low training error. And what we want is some guarantee that our learned hypothesis will have a good accuracy on the future on same examples, namely the generalization error. So here is the generalization error, the definition of the generalization error. So it's a probability that you make a wrong prediction for any input vector sampled from on the line data distribution. So now the strategy is as follows, right? Suppose I run some agnostic learning problem. Right? I got some model, I got some hypothesis in hypothesis space, I got some training error. So now I want to use this training error to describe about the generalization error of my learned hypothesis. So this is the goal. And how do we achieve this goal? How do we use the training error to bound the generalization error? Right? We're going to leverage a probabilistic inequality. So, which is also referred to as tail bounds. So basically, those tail bounds or probabilistic inequalities are quantifying or bounding the probability that your random variables jump to some low density regions. So if you take a look at those different curves that actually represent the probability densities for different types of random variables like Gaussian, like T distribution, and so on. Right? So we know that, okay, for any random variable, it is more likely it will appear in some region surrounding the mean, right? But if you just go quite far away from mean, that chance is getting very, very small. Right? But how do we quantify that small chance? How do we bound the chance that this random variable jumps very far away from the mean? Those are what hill bounds tell us. We can use tools of probability inequalities, hill bounds to do that. So now let us introduce several commonly used bounding probabilities. Right. So if you have taken any statistical class before, these bounds may seem familiar with you, and but please bear with me just to review those inequalities. So the first one is called Markov inequality. So it bounds the probability for a non-active random variable. So basically, it says, okay, for a non-active random variable x, the chance of x takes a value bigger than a is upper bounded by the expectation of x over a. So you can see, the larger the a, the smaller the chance, right? Because the smaller the upper bound of the probability. So this is called Markov inequality. A more commonly used inequality is called Chapter inequality. Because Markov inequality is kind of a single side, one-sided inequality. And Chapter inequality tells us, okay, what is the upper bound of the chance that a random variable jump away from its expectation or mean? So specifically, it claims that, okay, for any random variable x, its mean is mu and its standard deviation sigma. Then the chance that x is k standard deviation away from its mean mu, this chance is upper bounded by 1 over k squared. So we can see that the larger the k, the smaller the bound, right? Actually, the bound decreases quadratically along with the increase of k, right? So you can see, okay, if k takes 1, then the probability x jumps 1 standard deviation away from its mean is less than 1, right? Just less than 1. But if k is 10, right? If k is 10, then x jumps away 10 standard deviation away from its mean. This chance is less than 1 over 10 squared, 0.01. So basically says, okay, it's very hard for a random variable to take a value or jump to a place which is far away, very far away from the mean. Okay. Those are two commonly used hill bounds or probability inequalities, but here they are not applicable to our case because in our case we want to bound an average of random variables. How about the average random variables jumps away from the mean? We want to quantify that, right? Why? Because the training error is essentially an average of binary random variables, and its mean is the true error. So we want to bound the chance that the true error is far away from the training error. But as to why the training error should be viewed as an average of random variables, we're going to discuss about the reflex, right? So let us first look at the right probability inequality we want to use, which is called hope density inequality. So here's hope density inequality. Suppose we have m random variables. Those m random variables are IID, meaning that they are identically, independently distributed. And because they are IID, meaning that the expectation or the mean of each random variable is the same. So we can denote it by P. And now I'm going to take the average of these m random variables, right? So x1, x2, x3 plus together and divide it by m, right? So we got P bar. Now P bar here is a random variable, right? Because the average set of random variables is still a random variable. And P bar, we know that it is an empirical estimate of the true mean, right? The mean of those random variables. Now, hope density inequality tells us that your P bar, the empirical estimate of the mean, is epsilon away from your true mean. This probability is upper bounded by this exponential term. So we can take a look at this exponential term, right? It is e to the power of minus 2 m and epsilon squared. So m is the number of random variables you average, and epsilon is the distance. So basically it says, okay, the more random variables, IID random variables you average, the smaller the upper bound, right? Meaning that the chance your true mean is epsilon away from your empirical mean is smaller, right? And also this bound increases exponentially with the number of variables you want to average. So it decreases very, very fast. So basically you can imagine that, okay, suppose I have 1,000 examples, right? 1,000 random variables I just average them, okay, this term would be very, very small, so it might be just 0, right? And then let us take a look how this bound is influenced by this epsilon, the distance, right? So the larger the distance, the smaller the chance. Meaning that the true mean or the true expectation of these random variables is largely possible to be within the distance epsilon from my empirical estimate. If you increase this distance, I mean that chance is variable, and also this bound decreases quadratically, exponentially with the set of distance. So you can see that this is a very strong result. Basically emphasize that, okay, once you average a set of IID random variables, your empirical estimate of this mean has very high chance to be close to the true mean. That's what the hope density inequality tells us. Okay. So P here is the true mean, right? Like you throw a toss, you toss a corn, right? And you know the probability the corn you see the heads, right? This is the true mean. And your empirical mean is just you throw the corns for 100 times, for example. You just count how many heads, how many tails, and you got a ratio of heads. Right? Is your empirical mean. And the empirical mean will not be too far away from the true mean if there are many, many samples. That's what hope density tells us. Okay, so we're gonna continue with this. We're gonna use hope density inequality to get the sample complexity bound, the generation error bound for the agnostic learning in our next lecture. So And I wish everyone have a great fall break. And see you again